Hi, my name is Lars Rönnbäck, and the topic of this presentation is temporal joins and twines. While there's been quite a lot of presentations and literature around temporal tables, there's not nearly the same amount of presentations and material available for how to actually join tables that are temporal. So that's the reason behind this presentation. And this was based on work that we did back in 2018, I think it was, that resulted, or was part of a paper anyway, that we presented that's called Temporal Dimensional Modeling. We also made a blog post called Let's Twine Again that introduced a specific algorithm called the twine that we're going to be looking at in this presentation as well. So to start with, I'd like to talk a little bit about non-temporal joins, which is like a traditional join between two tables that have no temporality whatsoever. And the most classic case is, of course, when you can do an inner join. And in this case, I have two tables. I have a person table and a hair color table. And for each person row, there is also a row in the hair color table. So there's a one-to-one mapping between these tables. So I'm guaranteed not to lose any rows if I join these two tables together with an inner join. And the select query for this, you can see right there. It's quite easy. You just select something from a person table and you join it with the hair color on the key in this case. So it's a primary key in the person table and a foreign key in the hair color table to the person table. So this is something we're all familiar with. We also have a variant of this one, which is if in the hair color table you're not guaranteed to have a row for each of the rows in the person table. So as you can see here in this example, there's for person number 3, we're missing the hair color in the hair color table. So in this case, if we do an inner join, we will actually lose some rows, but we can remedy that fact by doing an outer join. So if you look at the SQL query up at the top again, you can see that instead of doing an inner join, we do a left join in this case, and still on the primary key and the foreign key in those tables. And if we don't want to show a null value for the hair color, for person 3 in this case, we can do some logic in the SQL query that replaces it with, say, the string unknown in this case, to indicate that we do not know what the hair color of this person is. And basically that sort of encaptures those two types of joins that we can do when no temporality is involved. So let's move on to an example where we have one temporal table. So hair color is something that is most likely to naturally change over time. Many people get gray hair when they grow older, and hair can also be dyed in different colors. So in this case, if you look at the hair color table, you can see that for person 1, they started out having blonde hair, and some 20 years later, this hair has turned gray. Whereas for person number 2, they probably dyed their hair purple for one day on the 11th of November 2011, and it was brown both before and after that date. And then we have person 3 in this case, where that person has had gray hair as well. And in this case, we're also guaranteed that there is a row, in at least one row anyway, in the hair color table for each person. So in order to still have a primary key in the hair color table, this key has to be extended in this case to include the valid from date. So in this case we have person ID and valid from in the primary key of that table. And person ID is still foreign key to person, and person's primary key is person ID. So it's a one-to-many relationship between these now. And the way we can do joins now between person and hair color is a little bit different now, because now we have to take temporality into account. And let's say that we want to ask what was the hair color of every person on November 11th of 2011. We should get something that looks like the result in the table. So for person 1, that hair color should be blonde, because if we back up here, you can see it was first in 2020 that the hair became gray. And we also know for person 2 that on that specific day that we're asking for, the hair color was purple. And for the third person, the hair color is gray. So this is what we should get. And the way we can do that is to first resolve the temporality within that temporal table that we have, to find what rows in that table were valid at that particular point in time that we're asking for. And one way to do that, there are several different ways. Most of them, if you have a good query optimizer, will actually result in the same execution plan. So here's just one example of how you can do it. You can do a subselect in the where clause with a condition saying that I want to have the latest valid from the hair color table where for each person, and I take the first or the closest valid from that's before the date I'm asking for. And that means that I will get back to a situation where I will have for each person ID just one row in this subselect I'm doing here. So when I do an inner join to this derived table from the subselect, I can do it on the primary key versus foreign key here. So it's an equi-join on the keys again. So I've basically reduced the problem of having a temporal join to a non-temporal join by actually first resolving the temporality of the temporal table. And this is quite a common situation. You usually, one of the most common use cases is to actually see things as they are right now. So you have like a current view of all of your data, even if you have it stored temporally. If we extend this to the other type of join that we looked at in the beginning, the outer join, we could have this situation also for a temporal table. So in this case, person number 3 again is lacking a row in the hair color table. So with the same reasoning as before, we can also here first in the derived table from the subselect find each row that was valid for each person on a particular date. This date is different here. You can see it's the 31st of December for 2001. And if we move back and check the table at the top there, on the 31st of December 2001, you can see that we should know what the, 31st of December 2000. We should see that the hair color of person 1 was blonde. Whereas for the person number 2, you can see that the first value that we're aware of with the brown color here is actually from 2002. So the date that we're asking for is actually before this first date, which means that we do not actually know what the hair color was at that point in time either. So that's why it's a null value for person number 2. And person number 3 didn't even exist in this table. So in order to produce this output, we do exactly the same thing, but we just switch from an inner join to an outer left join. So again, we sort of resolve the temporality first, and then we do a join, an equijoin on the actual key. However, there is a small thing here that could get lost if you're not careful. And as you can see here, I'm replacing the null values that I get with the string unknown in this case. But there are two types here of unknown. The first, for person 2, that hair color is unknown, not because I'm lacking a row for that person. It's because the first known hair color I have is from 2002, but there are rows for this person. It's just that I didn't know what the hair color was at that particular time. Whereas the other type of unknown is that I don't even have a row for this person at all in hair color. So if you want to distinguish between these two different types of unknowns, you actually have to extend the query. So you have one query for which you find a single row for each person that exists in the table. You do an outer join to that table. And then you have to do another outer join against all the distinct person IDs that you have in the hair color table in order to deduce if this person exists at all in the hair color table. So in this case, you get 2 equijoins, and with that, you can actually deduce and distinguish between these 2 different types of unknowns. Is it an unknown person, or is it an unknown time point in this case? So this might not be part of your use case, but if you need to make that distinction, then you need this additional pieces of SQL code in order to do that. So far, so good. And this covers a lot of use cases when you know that you want to look at the information at one particular point in time as it was, and you want to look at all the information at that point in time. However, things can get more complicated, and that's when we move from temporally independent joins, which we looked at, to temporally dependent joins. And looking at this example, let's say that for person, we also have a date, some sort of a date when this person became a member somewhere. That date is called member since. And now I'm not interested in the hair color at a particular time, a single point in time. I'm interested in the hair color that person had when that person became a member. That means that time now becomes a part of the join condition, because I need to join these tables where the time point is changing for every person that I want to look up the hair color of. So in this case, we have the inner join example again. So for every person, I'm guaranteed to have at least one row in the hair color table. So the only difference here is then asking for a particular date. I'm going to ask what color of hair did the person have when they became a member. So how would we normally approach this type of query? Well, one way to do so is to do a subselect from the hair color to get a range, a date range. So you not only have valid from, you also have valid to. And what you do is to introduce into the join condition itself. If you look at the join condition at the bottom from the subselect on the derived table, you can see that it's no longer an equijoin only on the person ID. You also have the time points as part of the join condition. So in this case, we cannot reduce this to a non-temporal join. The time points themselves become a part of the join condition. and I want to find the row for each person where this valid from and to is between, the member since date is between the valid from and valid to. And this is a type of query that doesn't actually optimize perfectly in most databases. There's no really great way to index this because the date is not an equijoin. It has to be between some values. Now, depending on your style of modeling, you may already have materialized this valid to date in the database. But if you look at many of the modern data warehouse techniques that are out there, they've moved towards being insert only, which means that you do not update any existing rows in your ETL flows. And that also puts a constraint that you cannot have a valid to date, because that's something that needs to be updated. If you get a new row, then the previous valid to will have to be end dated, meaning updates in the database. So I would say most modern data warehouses do not have this valid to column. And in fact, this lead operation that I'm doing on the hair color table is actually a very cheap operation to do, because while it's scanning the table, it's just going to keep one row in memory in order to produce this lead value. So it's while it's scanning the table, it's just going to use up the memory of having two rows in a buffer instead of just one row. That's basically it. So it's a cheap operation to do, actually. But like I said, the performance issue stems from the fact that you cannot do an equijoin anymore. So for each person ID, it actually will have to scan those valid from and valid to and member since and match those. So this performance degradation that you get will also get worse the more history you have amassed in your database or data warehouse. And this became sort of painful for us when we were doing that paper, Temporal Dimensional Modeling, where we had we had lots of example data that we wanted to work with and test out various performance, the different types of performance for slowly changing dimensions. And in that case, we sat down and looked at this type of query, and if there was any other way that this type of query could be done in a database. And that's when we discovered the twine algorithm. So basically what we are doing now with the join is to look at these two different timelines that we have for a person and finding the point in time. We have this point in time 2009, and we want to know between which points in time on the other timeline does this fall, in order to figure out that this is the period when this person had blonde hair. So we had one point in time on the member since timeline. There's one point for each person, but there could be many points in the valid from timeline in the hair color table. And it was when we were looking at the problem like this that we figured out that what if we combine these two timelines into one single timeline? And we call this combination of timelines a twine. So you get these time points on a single timeline, but in order to keep track of what type of time point we're looking at, we're also gonna number these time points. So basically we can reproduce the original two timelines if we would like by just splitting this twine based on the numbered timelines we have in the twine. And if we put them together like this, then the problem of actually figuring out which color is in effect, or since which date a color is in effect, is actually by just looking to the previous point in time on this timeline. For each number 2 type timeline, which is the member since, I'm just going to find the previous value, and I'm guaranteed that that previous value will be the interval of the color of hair that we're in at the moment. So this sort of twists the whole idea of doing a join into something else. So what we do, and I'm going to call this a specialized twine because it's not going to work for all cases, but in this particular case it will work. And with a twine, we do not have to do a join at all. So what we start by doing is to produce this joined, or this combined timeline by doing a subselect, that we do a union between those 2 different timelines that we have. Both have person ID. They have a number that is the timeline. They have the valid from, which is the time point in one of the timelines, and the member since, which is a time point in the other timeline. The hair color timeline will have hair color as values. There is no hair color in the person table, so I'm just going to add a null value in that case. And by doing this, we can use a lag operation. Like I said, it's the previous value if you look at these timelines. So I can simply do a lag operation on this combined timeline to find the hair color and the valid from, which were in effect at each point of type 2. So that's why I have a where condition at the very bottom, singling out that I'm just interested in that particular timeline. But I first have to do this lag operation on the combined timeline of both. So by doing this, I will get the table that you see at the top, indicating the hair colors and since, the member since date and when those hair colors became valid. So this is the idea behind this specialized twine. And you can also note here that valid 2 is actually not needed at all. There's no materialization being done of valid 2. So this also works well with modern type data warehouses that are insert only. There is also, for the temporal dependent types of joins, an outer join case. And in this situation, we are lacking information for person number 3 in the hair color table. But it could also be the case that in the person table, we're missing the member since. There could be some people that aren't members at all yet. So let's say that they have a null value in the member since table. So that's an additional reason for why a person might not have a match in the hair color table. So the question is still, what hair color did each person have at the time that they became a member? So looking at the first query, when we have this lead to create a valid 2 and the join condition that contains the time points themselves, we actually have this additional reason now. So if we need to keep track of the exact reason why the hair color is unknown, there's now 3 different reasons for that. It could be unknown because the person is not a member yet. It could be unknown because the person doesn't have a row at all in the hair color table. Or it could be unknown because the time point we're asking for is a point in time for which we didn't know the hair color. if you want to do this with the twine will actually look exactly the same, except that we need also to have some sort of indication of if a person exists at all in this timeline, in this combined timeline. So we can actually do that by introducing a conditional max that looks at timelines, the timeline 1, and just indicate if there is a value for a person in timeline 1, we're going to set this to number 1, or else it will be a 0. So that way we can know when we look at the information for each person if they had a row in that table or not. So with a small addition, we can actually do it in the twine as well. Now, when it comes to performance, this is where it becomes interesting then, because the idea was that we want to increase performance. And this is a comparison when you look at the outer join versus this specific twine at the bottom. And in order for this to actually be relevant, we added more data. So we have 1 million rows in the person table and 4 million rows in the hair color table. So what you see here is the execution plans that the query optimizer has come up with. And it's the actual execution plans from running the query. And when you put these two queries alongside each other and run them in the same batch, it will indicate how much time was spent on one query versus the other. So in this particular case, you can see that the cost of the query, the non-twine, like the traditional outer join query, is 63%, and the time for the other is 37%. In other words, the twine is almost twice as fast as the traditional outer join query. So maybe this was because we were doing an outer join, so let's just make sure that these results also stand if we do an inner join, and they do. So this is the execution plans for the inner join versus this specific twine. And as you can see, it's the same ratio here. So the twine is almost twice as fast as the traditional outer join. Sorry, in this case, inner join. So how is it actually able to achieve this? Because what's happening here? So the possible downside that you could have by using twines is that normally when you gain performance, you sacrifice something else. And for the twine, it seems to be the case that the thing you sacrifice in order to gain performance here is memory, because the twine will require some sort of sorting operation. When you join these two timelines, it will have to sort the data again when you perform this lag operation according to the timelines that you, the time points that you have in that combined timeline. So this is the trade-off, and which could of course affect performance depending on if you have maybe a few number of rows or lots of rows, or the particular database engine that you have could optimize this very differently from the one we're using here, which is SQL Server. Now, I call this the specialized twine for a reason, and it is because it works under specific circumstances. So let us revisit this temporally dependent outer join, but in this case we're gonna be using another date associated with a person. Rather than having a member since, we're gonna have a purchase date. And in this case, each person could have made more than one purchase. So we have a situation where we have for each person many dates, and many hair colors in the hair color table. But the question here is, what was the hair color at the time of each purchase date for these persons that we have? So for person 1, there will be 3 different hair colors because this person has made 3 different purchases at 3 different points in time. So now we're leaving the situation where this specific twine can be used. So we're going to be looking at a generalized twine instead. But first, let us look at what would this look like when we use the sort of traditional way where time points are a part of the join condition. And it looks very, very similar to what we did before. You have this subselect with a lead to get the valid 2. And you have the time point as a part of the join condition, and you perform left joins in this case. And this will give you the desired result, where you have the person number 1 having 3 different rows with 3 different hair colors associated with those purchase dates that we were looking at. So let us look at the twine then. And why this specialized twine can't work in this case. Because now we have many points in time for each person. And it could be the case, as in this example, that 2 of those points in time fall on the same interval of hair color that you have in the other timeline. So when you combine these 2 timelines, you see that you get 2 successive points of type 2, which means that this lag operation that I had just looking at the previous point in time no longer works. I cannot just look 1 step behind to get the correct time point. In this case, I need to also move back to the preceding time point with the additional condition that it is of type 1. It's in timeline 1. And that means I might have to skip 1 or many different time points of other timelines of other types or numbers. So the specialized twine with the lag operation no longer works in this case. So what we do is to introduce a generalized twine instead. And in order to figure out this time point of a particular type, we use a combined timeline as before, but we do not put the value in the combination or the combined timeline anymore. We only have the time points here. So we have the valid from and purchase date in the combined timeline. Then we do a conditional max operation. So we keep the maximum value of the time point for each person when we have this timeline of the type that we're interested in, so type 1. So this will be an accumulated max, since it has an order by clause also in the the window there. So it will be an accumulated max which will keep the previous and maximum valid from date in this case, since that's the timeline 1. And then once we've resolved these time points, we can actually make an equijoin towards this hair color table. So now it's not a between join, it's an equijoin, because you join on the person ID and the valid from with equal signs, which means that it can actually use this primary key index that we have in the hair color table. And we're still, of course, filtering at the very end to get those time points of from timeline number 2, which is those at the purchase date in this case. So this is the way we do a generalized twine, and that introduces as well this additional left join down at the bottom. but it is a left join on the primary key of the table you're joining with. So again, if we look at the performance for this, you can see now that the traditional approach is about as fast as the twine, actually very slightly faster. And in this case, we had 4 million rows in the person purchase table and 4 million rows in the hair color table. So here we are ending up in a situation where your mileage may vary, and you definitely have to test whether or not generalized twine will actually improve performance in this case when you do this. And since the paper came out in 2018, we've had lots of positive results from people having switched to using twines in their data warehouses. So it's definitely something that works in many cases. So you notice that in the twine, we actually ended up joining this hair color table. So a traditional join is involved, even if it's an equijoin on the primary key in this case, down at the bottom. But it is actually possible to avoid this join altogether by doing an additional max operation. So if we pick out the hair color as an attribute in the combined timeline and move that value up through the twine, we can actually produce this value without doing any joins at all. However, when we tried this in SQL Server anyway, this was slower than actually doing the join. So this was almost twice as slow as doing the join actually. So there's no guarantee that this is a good idea, but it could also be just putting it here so you can test it as one alternative way to do it. If you're in a database in which you really want to avoid joins at all costs, then this is one way you can actually do that. Now, finally, I want to talk about a situation where we have multiple tables. So in this case, we have added a table for the beard color as well as the hair color. So now we have two tables, and we want to know for each purchase every person has made, what was their hair color and beard color at the time. And we're going to do an inner join here. So, I'm sorry, there's the left join, sorry. But if you want to do that using the traditional way, you do this lead operation to find the valid 2 in both of these tables, and you get a join condition on both of these tables that involve these timelines. It's not an equijoin, so it's not very friendly towards indexes. And the way you would do this with the twine instead is to actually combine 3 timelines in this combined twine line, the twine itself. So you take all these 3 timelines and put into a single timeline. So now you distinguish between timelines of type 1, 2, and 0 in this case. And you do this with the generalized twine. You carry and find the valid from date for each of those timelines that you're interested in. So in this case, it's the valid from for the hair color from timeline 1 and the valid from of the beard color from timeline 2. And then we do those left joins that are on the primary keys in the respective tables, hair color and beard color in this case. And we keep only rows from timeline 0 in this case. So we get those purchase date time points and which hair color and beard color were valid at those points in time. So a single twine can be used to resolve multiple timelines. You can have any number of timelines that you resolve within a single twine like this. One thing that you have to keep in mind, though, is that since we're doing a union here of values, the first select statement that you have at the top there is going to decide the data types, at least in SQL Server, that's how it works. It's going to decide the data types of the other columns that you pick from the other timelines. So if valid from have different granularity in beard color and hair color, you have to ensure here that you are casting the values to a type that is granular enough to be able to represent both timelines. What are the conclusions then that we can draw from temporal joins and twines? Well, the first thing is that, well, temporal joins come in many different shapes and forms. If we decide to use twines, no end dating is necessary. It's not necessary in the other case either, but it's you will materialize some sort of end date on the fly there anyway. If you have this temporal one-to-many relationship, then you can use this specialized twine, which seems to perform better than the traditional type of join in every case that we tested. If you have this temporal many-to-many relationship, you will have to move to a generalized twine instead, in which the performance seems to be about equal in the tests that we made. So I encourage you to test whether or not it will improve performance for you. And if you use those generalized twines, you can also extend them to resolve multiple timelines in a single twine. So if you have many temporal tables that you need to join together, then this can be done using a single twine in that case. All right. So that's it for temporal joins and twines. Thank you very much for listening.